Wow, when the lights come up, you don't look like Mr. Baldwin.
And you don't look like Mrs. Awad.
Well, that's a good observation. Wow, if you haven't met Mr. Z, I'm Mr. Bin. We're the other teachers who get to help you learn about this exciting subject. So we're in segment 2 now, right?
We are. We're getting started with segment 2. And we have the segment 2 learning objectives, which is a pretty lengthy list. And instead of Mr. Bin and myself boring you by reading all 12 of these, we're going to suggest that you pause the video now and go ahead and read those to yourself.
Okay, welcome back. Atlantic Ocean floor topography. Ooh, topography, that's a big word. That looks like a good words for friends kind of word, doesn't it?
Yeah, it does. It does. What does that mean, Mr. Ben? Topography.
I think when we did our sketches outside, wasn't that kind of like the lay of the land, how things look when they're out there?
Yeah, and kind of almost like a change in elevation, right? So maybe a hill compared to a lower piece of land or a flat piece of land. There's a difference of topography there in elevation. So,
like it's pretty flat around here. If you drew the topography here, wouldn't it kind of be pretty flat?
It would, and if we were to continue west towards the Rocky Mountains, we probably wouldn't find that because that's a higher elevation. The topography changes, the landscape changes. It goes up in elevation.
I wonder if under the ocean, it's totally flat.
Well, I think that's what a lot of people thought up until World War II with the use of sonar and finding submarines, which actually kind of led us to this idea that the bottom of the ocean isn't flat. And let's take a look at this graph because that's what it actually illustrates here.
So this would be like over at the, like in Florida, North America.
Yeah, well, along the coast, right? Okay, so that's, all right, we've got Florida written up there.
So it's kind of flat when you come offshore where you're wading in the ocean and stuff, and then what? It drops off, gets a little deeper, and then all of a sudden, ooh, that's a big change.
Yeah, and you know what? We should actually take a look at these words down here at the bottom and start actually putting those into the graph. So let's just go ahead and read that. Describe the characteristics, features of the ocean basins, right? Label them on the profile from Florida to Africa. All right, so we've got Florida all the way over here, right? We can picture that as the east coast of the United States. And then we've got Africa all the way over here on this side. And we can picture this as almost like an outline of the bottom of the ocean. Right?
Looks like they're not in order exactly how you're going to place them, so you kind of have to know what you're doing. Now, a shelf, like you put a book on, what shape is that, Mr. Z?
Oh, it's just kind of like flat, almost like a right angle.
So it's probably going to be someplace on the diagram where it's kind of flat.
Yeah.
Probably right near shore?
It is near shore.
Okay, so near Florida, we're talking about the shelf, continental shelf. And then I do the ski club, a little endorsement for the ski and snowboard club. We like to go on slopes. So this looks like a double black diamond slope. So would this be the continental slope, kind of going down steep? Okay, so we've knocked out the shelf and we've knocked out the slope. And it looks like we've got a section here where it slowly rises from the deep part of the ocean up to the slope. I wonder what that would be called.
I don't know. I'm going to take a shot in the dark and say that it's the rise.
Ah, that's a good name for it because it rises from here, which would be like the deepest part, of this section of the ocean going up. So it's kind of, if you take an average, you got a rise, you got a steep slope, and a relatively flat spot.
And then we kind of move into this just like vastness of this flatter area, right? And it may not be as clear in the diagram, but if you really take a look here at the x-axis, we're talking 500 or 600 miles of just not a whole lot of topography there, or a lot of change in elevation. And we're going to call that the abyssal plain.
So the plain part is kind of flat, it's kind of really deep.
And think about the plains of the Midwest, right? We can look at it that way, very flat. All right? So we've labeled these on our profile, but
should they do this on their papers too?
They definitely should do this on their papers.
This is something that could show up later, couldn't it?
Yeah, but you know what's, something's, really interesting. There's kind of like a big mountain in the middle of the ocean. I wonder what that's all about.
I bet Wegener didn't know about those mountains.
No, he definitely didn't know about that. Maybe it has something to do with that mechanism he was searching for.
Probably does.
You know what? This next slide actually has a really good video about the topography of the ocean floor and how they actually map that.
That looks like an initial. Could that be mid-ocean ridge?
It could be.
That's the thing you're talking about in the middle of the ocean, a
That's
ridge
it.
of mountains?
That's it, the mid-ocean ridge.
And so then once you get to the mid-ocean ridge, it looks like it's not exactly a mirror image, but it looks like you're going to the abyssal plain. You've got the rise, you've got the slope, and then it looks like it's a little cut off. It looks like the shelf would be over there. So almost like a mirror image, but starts with the high spot, the mid-ocean ridge, moving on over.
Mm-hmm.
Boy, you think the students are going to be able to grasp these concepts?
I think they should. I got confidence in them.
I do too. We've got some great kids.
All right, let's play this video. All right, well, we can't play it here for you, but you can pause this video, and on the same page that you're watching this video, you'll see the slideshow, and you should be able to watch it there. So pause this video
and go up the slide
and
deck.
go up to the slideshow, the slide deck, and go ahead and play the video.
From the actual from the Google PowerPoint. Okay? And then they can come back to us after it's done. Okay. See you in a few minutes.
All right, and then make sure that you draw a diagram that summarizes the process of mapping the ocean floor.
So they should do
Make
this.
sure you get that down.
So they should be thinking about that during the video and then have that drawn before they come back to us.
Exactly.
Sounds like a plan. Ooh, Mr. Z, do you think their diagram looked like this?
I hope it did. I really hope it did.
Well, if they've got lots of colored pencils, I think they probably have one that looks like this. This looks like that GIS thing we were talking about.
You know what it does from the last segment, and if you remember, we had a similar map, and we had other layers on it. We had layers that talked about fossils. Mm-hmm. We had another layer that had
glacial deposits.
Deposits. We had another layer that had rock types.
Mm-hmm.
Right? So this is another layer that's showing rock ages.
Okay, so let's see if they get the grasp. This is South America, right?
I think so.
Yep, and North America.
Definitely.
Okay, and that would be Africa.
Africa's right there, got it.
Okay, and Europe and Asia.
I see them both.
Okay, so basically they've really downplayed the continents, so they must be wanting us to look at something else. What could this colored stuff be?
Well, it looks like I've got a 0 all the way here on the left, and then I've got a 90 over here, and then I've got 100, and then, oh, wait a minute, it tells me exactly what that is, right? It says seafloor age in millions of years, right? So that means that anything with this kind of like whitish color or off-white is 0 million years.
Like new stuff that just came out of the
well,
Earth?
you know what? Remember, in geologic time, that's 1 million years is really not that long.
Okay.
All right? It's not that long at all. And then we go at different colors over here. We go to 90 years in this kind of aquamarine, right? And then we see that these darker red or maroon colors are the oldest rocks at 100 million years old. I think that's a lot of stuff going on in that map.
I think I'm seeing a pattern here, Mr. Z.
Okay.
It looks like right here, this is where that abbreviation, what was that abbreviation with the M?
M-O-R.
Yeah, more. Mid-Ocean Ridge.
Mid-Ocean Ridge.
So coming out of the Mid-Ocean Ridge, it looks like these are the newest rocks, the ones that are less than maybe 1 million years old.
Yeah, and you know what I noticed too is that the further away I move from the Mid-Ocean Ridge, away from it in either direction, right, I notice that the colors are the same. So where it's red on one side, it's red on the other. Purple on one side, purple on the other, and then so on and so forth. So it seems that the further away I move from the Mid-Ocean Ridge, the older the rocks get.
That's what it looks like to me. I bet Alfred Wegener would have loved to have this kind of information.
Definitely. And I would definitely write this down on this map right here, that not only are the rocks getting older, but it seems that the same distance moving away from that mid-ocean ridge in either direction. The rocks are the same age or just as old moving away.
So it's symmetrical, it seems
Yeah.
like, where you've got two chunks here, and they're just as wide as on each side. And over here, same thing, where you have the teal being coming out. You've always got about the same size.
So let's take a look at this question, because we just have to make sure that we're answering this correctly, and just so we're all on the same page here. How does the oceanic crust age distribution in the Atlantic Ocean basin support sea floor spreading?
Okay, let me see if I got this
Seafloor
right. Let me
spreading.
break it down. Basin's like bowl, right?
Yeah.
So they're trying to say, how does the oceanic crust age distribution? So how does the age in that basin, how is that supporting this idea of seafloor spreading? Well, this would be the basin between the land, right? Okay, so what could be a mechanism that would have the land be together at one time and moving apart? Could something be coming up and pushing the material away?
It definitely could. If we have molten rock or newer rock, right, coming out of this mid-ocean ridge, pushing the continents away from each other, right, then the further away they were, the older the rocks are going to be on either side.
Okay, so way back when the land was once together, then there was a crack maybe right between it. And then slowly material came up and then kind of pushed equally away. And it would have deposited the next. And then to make room for the next, it would push even more.
I would agree with that.
So it continues to push equally in opposite directions, constantly making that ocean bigger.
And we've already seen this continents, or all the continents already pushed together from the first segment, right? What was that called again?
Pangea?
Pangea.
Okay.
Right? And that accounted for the fossils, the glacial deposits, the rock types, and everything that we've already mentioned from segment 1. This is the mechanism that Alfred Wegener was searching for. We're starting to understand that, or at least to get more evidence to support it.
So this is a big piece of the puzzle, a big way to explain that seafloor is spreading through the age. Oh, it looks like this one, same kind of information, but if you notice, there's a different layer on. The layer that's on has an eyeball on it, and that's one thing you'll pick up the more you use this program. If you want to change and see different things on the screen, you just have to click or poke the eye. And if the eye is on, you can see it visible. That's the layers or layers on the screen. So now we're looking at earthquakes. We're looking at earthquakes that are what? 4.5 to 5.9.
So they're pretty shallow. In terms of earthquake terms, they're pretty shallow.
Or the depth. Yeah,
The
the
depth.
depth is shallow.
Yeah, so let's take a look at that. Earthquakes. Now, I mean, we live in Chicagoland area, and we've had a couple earthquakes, real little ones, but not real big ones. Not as big as my cousin has in California, that's for sure. You know, and I've got a lot of relatives in Greece, and they got a lot of earthquakes too, and you know, we don't have earthquakes like that over there. So, you know, but what I'm looking at here is that all these earthquakes, they kind of make like a pattern almost.
Okay.
They kind of, I can see a kind of a line in the middle of the Atlantic Ocean. Do you see that, Mr. Ben?
I do. This really light line. It looks like the earthquakes they have there, they look like they're relatively shallow depth.
And you know what? From the last slide, that's where all those newer rocks are.
Okay, so maybe what's happening is it's kind of like the Earth heals itself, and then it has a pressure, and it ruptures right on the surface, and that lava you said kind of comes out.
Yeah, you know, could that rupturing cause an earthquake?
I bet it could.
Yeah.
Kind of like it holds, and then it splits right at the top,
Yeah.
and the new lava comes out.
Huh. And that would kind of make a lot of sense to where all those earthquakes would be right along where that mid-ocean ridge exists.
And they'd be right at the surface, right where the rips was happening.
Yeah, really shallow.
I wonder what could be happening here, because it looks like they're shallow kind of at the edge, and then they go deeper as you go in. Wait, this makes another question I'm thinking of. If this ocean, we said, was getting bigger all the time, and the Earth isn't getting bigger as well, that must mean what comes up somewhere must
Go down.
Yeah, because the ocean. Wait, one ocean maybe is getting bigger. One ocean maybe is getting smaller. Where's all this material that's coming up? Somewhere else it must be going down.
I don't know. I'm sure we're going to talk about it in a different segment or later on in this segment. So maybe we shouldn't get too ahead of ourselves, Mister. You know, we're too excited about this
Yeah, I
information.
think we are. So I think what's important is explain the distribution of shallow earthquakes. They're, like you said, the mid-ocean ridge. You find a few of them scattered around. Greece has a few a little bit deeper. It looks like kind of where the land comes together, some continents.
Yeah, but you know, then what's funny, these earthquakes, it's where they're occurring seems to just follow all these lines. And you know what, maybe that's going to be important later on. You know, let's continue on. Maybe we can find another layer in GIS that'll help us out with this.
Yeah, maybe one of those. Volcanoes. We always like in science to base one idea off of another. Let's see if there's anything, you know, with volcanics that kind of back up, you know, what's going on with our earthquakes. So we've got, in green, we've got a series of volcanoes here that kind of make a shape like what you're saying. We've got a little arc, it looks like. Okay.
And we've got a couple of them scattered here in the Atlantic Ocean, over here.
But I see a ton of them up there in Iceland. So,
yeah, I do see a lot up there.
So why is there so much volcanic activity in and around Iceland? If we had another layer on that showed that that layer with the earthquakes, or if we had a layer on that showed the mid-ocean ridge, I bet it would go right through Iceland.
It would too.
I wonder if Iceland is just kind of like where when it rips, extra lava comes out, and it's so much it makes a mountain that sticks out of the ocean.
Yeah, I bet you that's what's going on there.
Okay,
so we have the mid-ocean ridge that we've already identified from the previous slides on here in red, right? And we've kind of drawn that, and it actually runs right through Iceland.
That's pretty amazing.
It is. And Iceland's known for a lot of volcanic activity and geothermal activity, they do a lot of that kind of stuff. And you know what? There was a huge eruption in Iceland like 4 years ago.
Yeah, I believe there was.
That shut down all the airports in Europe for
Some of my
like
students
3
couldn't
weeks.
go home.
You know, I had a couple of students too that were actually stuck in London at that time.
This is pretty exciting stuff.
It is. Another GIS layer. I mean, we just work with this program so much in geology because it's so useful.
But I bet if you keep looking at these layers and keep seeing these patterns, you can get a pretty good idea of how things work.
Definitely.
Again, Wagner would have loved this.
So let's take a look at this. Why does the depth of the ocean increase with increasing distance away from the mid-ocean ridge? So we've got another layer here. We have the depth of the ocean with the greater depth being in darker blue, and this is more shallow, which is kind of this lighter color. But you know what this is reminding me of? It's like 5 or 6 slides ago when we were identifying the topography of the ocean floor.
Yes, it
right?
is.
And we remember we had the slope and the shelf on either side, right? Off the coast of the United States and off the coast of Africa.
And then when you got near the middle, the mid-ocean ridge, isn't that where you said there was like a mountain range
Yeah, there
coming
was
up?
like a mountain in the middle. And you know what? What I see is that this shallow, which is illustrated in white, kind of runs along this line. And I'm seeing this same line over and over and over again. Every single slide we see, I just start to see this line over and over and over again. I wonder what it could be, Mr. Ben.
Hey, and it goes right through Iceland again. I bet if we keep going through this slide deck, we're going to figure this out. Wait, divergent plate boundaries. Diverge. That's like when you cut something, you divide it. So divergent means the plates are going apart, right?
Yeah, well, it's moving apart. It's like the opposite of convergent, which is coming together. So we're moving away from each other. Well, what's moving? Well, now we're talking about plates here. So then if we have a mid-ocean ridge,
like here,
right like there, so then we must have a couple of different plates there too, right? I mean, if it's a plate boundary, so this is kind of the boundary between two plates.
So over here would kind of like be where North America was, right? Or South America, and over here would be kind of Africa.
Yeah,
All
yeah,
right.
you're right. But this is now talking about magnetic anomaly patterns. Wow.
That's like a compass, isn't it?
It's kind of, yeah, you're right, it is. Because what exactly does a compass measure? Right, it's the magnetic field lines.
How strong it is. And your magnetic minerals point towards either they always point towards the strongest magnetic pole. So I wonder if on the Earth, the North Pole has always pulled just as hard. I don't think it does.
No, it hasn't pulled just as hard, and we know that, and this actually proved that not only did it not pull as hard, but then there were also polar reversals that we're actually overdue for, that people are kind of scared of.
So that after they watched the last segment and they had to make their map, and I said, hope if they had colored pencils it looked just as good, and they had different stripes, that looks kind of a lot like this, just not as colorful. So Mr. Z, if I'm reading this right, when lava comes out, maybe not only is this the same age, but maybe the magnetic minerals are pointing in the exact same direction at that time.
You know what? I think so, and I think that's what they discovered, taking core samples of the rocks of this area, that they noticed that all of the crystals in these rocks, right, were all pointing in the same direction because of the magnetic field line at the time. But now, if I take a look just to the left on either side of the ridge, right, the magnetic lines, the crystal lines, the magnetic crystal lines are pointing in the opposite direction. What does that tell us?
Well, I guess what maybe the scientist said is whatever way the minerals are pointing now, that's normal. So we're going to call that normal.
Okay.
So if the North Pole is really there, then that's normal. So maybe when the rocks came out way back when, the minerals were pointing south.
They were reversed.
Okay, and then they looked not only at the ages, and they found that the ages matched, but all these minerals in that lighter color, again, they pointed back north. And then they went a little bit further, same ages over here, and now they're pointing south. And so, like a clock, it kind of flip-flops back and forth. This would support that age idea that we were talking about earlier.
Yeah, you're right.
So maybe so where does this diagram fit in the Atlantic Basin? This would be, you said, right in the middle, right?
This would be the mountain range that we've talked about, the mid-ocean ridge, which is right here, right? And the further I move either this way or that way is the closer I get to the continents, right?
And the symmetrical patterns of age and magnetic minerals as you go away.
Yeah.
So this would be like way back when, in the beginning, like maybe Pangea time, and then this would be a time later, and then this would be like nowadays.
Yeah, so if you would think of that diagram far away, right, or kind of like in the background, that would mean that the continents were closer together.
So that would be kind of like South America and Africa touching.
Yeah, or really close to each other, exactly.
And then like a rift or a rip broke between them and separated them. Okay.
And then this middle picture is they've spread out further, right? Millions of years have passed at least.
And the whole time lava's coming up and keeps shoving them away.
That process is never stopping.
Okay.
And then this last picture is that they're even further apart, and we can see the polar reversals within the rocks. Again, another piece of evidence that this has been taking place for a long time.
I keep going back to Wagner with this, but I think he would have never had that idea of continental drift if he knew all of this. I think he would have known it's not continents drifting. It's something to do with those plates you keep talking about.
Yeah, you're right. And something to really think about here is that this data is relatively new. This is not something that was discovered hundreds of years ago.
Right, you talked about World War II, that guy Harry Hess, that's when he that's when he left his sonar device on, and he was able to get this information. So this is like the 60s.
It is,
They had to rewrite textbooks, I think.
They did. You're right. You're absolutely right. All right, back to it, everybody. So we're here and we're still talking about the magnetic anomaly patterns. And I think, Mr. Ben, I think we've done a really good job thus far presenting a ton of material in this segment. A lot of stuff that we covered. Hundreds of years worth of geology just wrapped up into 20 minutes of a video. So, you know what? We've talked about a lot of different things here thus far. We talked about continental drift, mentioned Alfred Wegener a lot. We've talked about plate tectonics as well, or starting to introduce that. You know what? But there is a difference between the two. They're not the same.
Right. We've talked about some evidence, and I kept interjecting in there things that Wegener would have loved to maybe have seen. And I think it's important to keep in mind, and they should look back in their notes at all those different GIS programs and the pieces of evidence that help show this. So maybe we can go to the mastery check at this point.
Yeah, and you know what I really like to do, especially when I want to compare and contrast something, is I really like to create Venn diagrams.
Oh yeah, nothing's like a good Venn diagram.
And T-charts. It just really puts it into a visual for me so I know exactly what's what with each of those topics. So let's get to that mastery check. All right, the mastery check is compare and contrast continental drift and plate tectonics. So those two things that we've been talking about.
So Wegener, he's the continental drift guy, right?
Yeah, yeah, he is. And the plate tectonics came from his theory. But remember, he didn't have the mechanism.
Okay.
So that's a little bit more the plate tectonic side.
So the plate tectonics, that's going to be more the evidence that we've been looking at on GIS.
It is. So the earthquake data that we saw.
Right, the age of the seafloor.
Yeah, the topography of the seafloor as well.
The magnetic anomalies showing the reversals.
Definitely.
I think those are the biggies.
I think so too. So to do this, you may want to make a Google drawing, a Venn diagram or T-chart to demonstrate your understanding of the similarities and differences between continental drift theory and plate tectonics. So that is the mastery check for this evening.
Yeah, I like that Venn diagram. So things that are common go in the middle, and the way that they're different go on the ends. Which is your favorite, Mr. Z?
Yeah, I like the Venn diagram too, but that T-chart though, I've really found that useful. Right? And it's really just creating a T and putting each one of those topics on either side, and then the characteristics of each.
So like all the things about continental drift would go here, and plate tectonics, all the characteristics would go there.
Exactly. It's just that simple.
I think both of those would do a pretty nice job. I'm excited to see what the students come up with.
I am too. Very excited.
I can't wait to the next section.